So I'm going to show you how you get this 4x frequency in the next slide by asking the question, how many racks or how many servers are required to actually process a modern real-world video-heavy web service. This could be a social media app. It could be a video on demand application or a streaming application. Doesn't really matter, because what I'm asking is if I put a consistent load on a set of servers, as I was just talking about, then how many servers does it really take to process that load? And in this case, I'm asking for 1.3 million requests per second. This is a very modest load for a web workload. And in this, looking at a video heavy workload meaning it's processing a lot of video in parallel with all of the other services that are required to actually stand that service up. And if you look at a modern web service, they're very tiered. And these are the typical tiers that you'll see. You'll see a web front end as characterized by something like NGINX. This is probably one of the most popular containers in the world today, followed by caching layers, because caching actually reduces latency, it reduces jitter, it gives a much more predictable profile by putting the most commonly accessed elements into high-speed memory caches. And things like Redis and Memcached, Cassandra, all of these sorts of kinds of technologies are very, very popular for doing this type of thing. To round out my video workload part, we're going to be doing some transcoding here. Now, in this case, we're doing the transcoding on the actual CPU for this particular example, but you could use an even more power efficient technology like NetInt. This is one of the reasons why we're such good partners and such a good pairing of companies, is because we're both producing silicon technology that can actually make the whole solution more power efficient. I actually used H2.264 here to kind of build out that kind of 20 to 25% of the total capacity of this workload is doing actual video transcode. And then finally, you have a backend in MySQL that allows you to kind of do persistent storage, right? Which is of course required, and that's a major element of this kind of tiered web application. Now, coming back to my point about 4x efficiency, what you're seeing in these graphs is performance per watt, which is the measure of that efficiency. How much am I getting out of my NGINX engine in terms of queries per second or requests per second per watt in the platform? And you can see here that in this example, we are providing almost 5x better performance per watt than comparable x86 solutions. This is the difference of using a cloud native architecture. Now, it goes down from there, but NGINX just happens to be a very compute bound workload, and it hits all of the kind of sweet spots in a scale out compute intensive architecture like ours. But other workloads get the same or similar kinds of efficiencies. Redis, which is a key value store, almost 4.5x. The transcoding itself, almost 3x. MySQL, about 2x. Why do you see this variation? Because all of these different workloads exercise different parts of the architecture. If you're looking at H.264, this is a very compute-intensive activity, as the NetInt guys can attest to. You put a lot of computational horsepower into this. In MySQL, you're going to be very I/O bound. You're really going to have a lot of interaction with disk or drive, and whatever the storage infrastructure is that's persistent behind the web service. So that actually limits the benefit that you might get out of these scale out efficiencies that we're putting in here. But still, you get a benefit, almost 2x better. So if you combine this whole thing up and you look at the actual results of this, then efficiency is measured in power consumption. In other words, just use less power. How do you use less power? You do it the same amount of work in fewer components, and you burn less power on each component when you do it. That's the power of this architecture.